Hi, everybody. In the name of God, I'm GHARAEI, Associated Professor of Anesthesiology at GHARAEI, University of Medical Sciences, Tehran, Iran. In these slides, we are going to cover some topics including atmospheric pressure, partial pressure of gases, how air travels to the lung, and what would be the partial pressure of gases in our alveoli. After these, in other lectures, we will learn how oxygen will be carried to the tissue and then carbon dioxide will come back to the lung. During these kind of slideshows, I really recommend you to be interactive, to learn more. To be interactive, I ask you, when you come to the gray boxes with questions, pause the film at that stage and start thinking and solving the problem yourself. And also, I recommend you to watch this film with your colleagues. In that case, you can have some discussion during watching film. Thank you for being with me.
Okay, how to use these slides? It's a narrated PowerPoint designed for medical students. In each section, some questions will be asked, and I really want you to stop the film at that stage and try to find the answer yourself. The answers should be discussed by peers and colleagues if possible, and if there is any problem with the questions, you can email to me. The email is provided in the slide. In our hospital, after watching these slides, students are asked to attend a 1-hour session of a small group discussion, which is totally different from the slides. And we hope by these small group discussions, they can reach higher levels of cognition. Our students, after completing several sessions, are finally asked to evaluate a real patient at bedside with a respiratory problem, and if they are successful in evaluating the patient, then they will be accredited accordingly. We show you the goals of this session, which is the first session of this series. In this session, we are going to talk about atmospheric pressure, partial pressure of gases, how air travels to the lung, partial pressures in alveoli, and finally, we have one slide with some questions that helps you evaluate yourself. You also find in this slide the number of slides related to each topic, also the range of minutes which will cover these topics in the film. The first topic we are going to discuss is atmospheric pressure. To start the topic, I would like to ask a question. What will happen if you put a straw in a cup of tea? And do you think that tea will rise up within the straw? If you close the end of the straw, the upper part of it, and bring it up, what will happen to the tea inside the straw? Will it rise with the straw, or will it remain at a level of tea outside the straw? I would be very pleased if you could think over these questions and then go to the next slide. As you saw in the previous slide, in the film it was shown that when the straw end is open, tea doesn't go up, the level doesn't change. But when the straw end is closed, Atmospheric pressure will not affect T inside the straw while it puts pressure on T surface outside the straw. The pressure on the surface of T is called atmospheric pressure, and the difference between outside and inside the straw will cause the T level to rise up within the straw. In this slide, you can see when you have a container full of fluid, then the atmospheric pressure on all surfaces at the top, bottom, lateral side would be the same. But inside the container, as you have some fluid, then in addition to the atmospheric pressure, you will have the pressure induced by the column of fluid. As you can see in this picture, on the left side, you have a straw which is not closed. Then the inside and outside the straw will have the same atmospheric pressure, and the level of fluid will not change inside and outside. In the middle figure, you can see that we have closed the end of a straw and brought it up, but not more than 10 meters of water or equal to 760 millimeters of mercury. So you will not have empty space at the uppermost part of the straw. But on the right side, you can see that you have a tube. It is a closed one and it is very long, and you bring it up more than 10 meters of water if the fluid in the container is water or tea, or more than 760 millimeters of mercury when the container contains some mercury. So in that case, you will have some negative pressure, which is at most 760 millimeters of mercury, which is equal to 0 Pascal pressure, or we can say relatively it has a -1 atmosphere negative pressure over there. In this slide, you can see how to convert the dimensions of pressure. You can see that 1 atmosphere or 1 bar pressure is equal to 760 millimeters of mercury, which is nearly equal to 10 meters of water, 100 kilopascal, and it is equal to 14.66 psi. Okay, we have come to another gray box question. In these questions, we are going to learn how to convert pressure units. The first question asks, if the oxygen cylinder has a pressure of 2200 psi, what would be its pressure in atmosphere and millimeters of mercury? The second question asks, to connect oxygen to anesthesia workstation, it should be 50 psi. What would it be in atmosphere, bar, and millimeters of mercury units? Okay, as we discussed, we know that we have something called atmospheric pressure. But what really causes atmospheric pressure? The Earth has gravity. The air has weight. This air weight causes pressure on any object on the Earth. It is called atmospheric pressure. So, what causes air to have weight and produce pressure? I would like you to stop at this stage and think over this question. As you know, components of the air
are oxygen and nitrogen. In other words, air consists of molecules. Molecules have weight. Air approximately consists of 21% oxygen molecule and 79% nitrogen molecule. Then we come to this question. If the weight of oxygen atom is 16 grams per mole, and for nitrogen atom is 14 grams per mole, what is the weight of 1 liter of the air? There is a clue here. Each mole of a stable molecule in its gaseous form will have 22.4 liter volume. You will have enough time to calculate the weight of 1 liter of air. I'm sure you could calculate the weight of 1 liter of the air. As you know, air consists of oxygen and nitrogen. So each liter of the air will have 0.2 multiplied by molecular weight of oxygen over 22.4 plus 0.8 multiplied by molecular weight of nitrogen over 22.4, and the result would be about 1 gram. So each liter of air has a weight of about 1 gram. The other question, which is really difficult, as I understood in my classes, this question may be very sophisticated. I want to ask you this question, but if you are unable to answer this question, do not worry. It is common. Having the following information, pressure of 1 Newton per square meter is equivalent to 1 Pascal. Atmosphere has a pressure of 100 kilopascal. Earth gravity is about 10 meter per square seconds. Therefore, each 100 gram on Earth is equal to 1 Newton. Then, what would be the height of atmosphere? I know it is really difficult, but you can solve it. The answer you find will be the amount you calculate is mainly troposphere, which consists 3/4 weight of total atmosphere. Okay, I hope everything is okay till now. Till now we understood that air has weight and this weight causes pressure on the objects on the earth. Now we come to another concept which is called partial pressure of gases. As you measure the 10-kilometer troposphere will put pressure on us called atmospheric pressure. But the question we are going to answer now is what proportions of this pressure is caused by oxygen and nitrogen. As you can see in this slide, we have a formula called Dalton's law. It says that partial concentration of a gas over the total volume of the gas is equal to the partial pressure of the gas over the total pressure of that gas in a fixed temperature. In other words, as you can see in this picture, on the left side, 0.2 mole of oxygen in 1 liter plus 0.8 mole of nitrogen in 1 liter. If they both come together in 1 liter, will cause a pressure equal to the pressures of those gases each had. Okay, in this slide, we come to an actual situation. We are continuing our discussion over partial pressure of gases. We saw the Dalton's law in a diagram. Now we come to an actual sample. When the air has a pressure of 760 millimeters of mercury, then 160 millimeters of mercury will be for oxygen, which consists 21% of air, and 60 millimeters of mercury, which is 79% for nitrogen. Now we come to another question to know whether we understood this concept well or not. The question is, if we use a humidifier in a room to increase the humidity to about 60 millimeters of mercury, what would be the partial pressure of gases, water, oxygen, and nitrogen in this room? Please pause at this stage and once again think about the partial pressure rules to find the answer of this question. So as you see, adding a new gas will change the partial pressure of previous gases. I'm sure you found that when we have 60 millimeters of moisture in the air, then this pressure, which is 60, will be reduced from 760, and the remaining part, which is 700 millimeters of mercury, will be divided proportionally for oxygen and nitrogen. Now we come to another question. Now in the same room with a humidifier with 60 millimeters of mercury, we are burning some papers which causes 1% carbon dioxide gas. A clue here is this partial volume or partial concentration of the gas is in the whole room, which means 1% carbon dioxide will cause 1% of the total pressure for carbon dioxide pressure, which will be 7.6 millimeters of mercury. Then, what would be partial pressure of oxygen, nitrogen, water moisture, and carbon dioxide in this room? I would like to ask you to spend some time thinking on this question because it is a very crucial point here, and then go to the next slide. Okay, I hope you are not tired yet. So we are continuing our discussion about partial pressure of gases. We had a very difficult question. And now to answer the question. One can say that water will proportionally reduce all other gases as it acts independently. However, to produce each molecule of CO2, one molecule of O2 or oxygen is consumed. Therefore, carbon dioxide will just replace oxygen and will not affect nitrogen. So it is totally different from water. So we can subtract water from atmospheric pressure. As you saw, we had 60 millimeters of mercury water moisture in the room, so we have 700 millimeters of mercury left for other gases, which are oxygen, nitrogen, and carbon dioxide. So the remaining partial pressure would be for nitrogen with its previous partial pressure of 79% and new partial pressures of oxygen plus carbon dioxide. So As you can see, by multiplying 79% by 700 millimeters of mercury, we come to 553 millimeters of mercury partial pressure for nitrogen in this room. In other words, nitrogen plus water moisture will be 553 plus 60 or 613. Deducting this from 760, we will have 147 millimeters of mercury for the sum of carbon dioxide and oxygen. As at the first place we had 1% carbon dioxide, it means 1% of 760 millimeters of mercury is for carbon dioxide, which would be 7.6 millimeters of mercury. So finally, oxygen will have a pressure of 147 minus 7.6 or 139.4 millimeters of mercury. We are continuing our discussion on partial pressure of gases. We come to the point that we found the partial pressures of carbon dioxide, oxygen, nitrogen, and water moisture in the room that we were discussing. So we come to another method to find the answer. In this method, you can see that final oxygen partial pressure is equal to initial oxygen partial pressure multiplied by water pressure reduced from atmospheric pressure, then the total result. From the total result, we should reduce the partial pressure of carbon dioxide. Therefore, as you can see, the final oxygen partial pressure in our example would be 21%, which is the primary oxygen partial pressure in the room, multiplied by the remaining part of the pressure, which does not include water, which is 760 minus 60. And then from the total amount, we should reduce the carbon dioxide pressure, which is 1% multiplied by 760. So the result would be 147 minus 7.6, which is 139.4. So as you can see, this formula will help you find the final oxygen partial pressure in a condition that you have a gas such as water, which will reduce proportionally other gases such as nitrogen and oxygen. Also, it includes some gas such as carbon dioxide, which will just replace oxygen and will not affect nitrogen. Okay, we can show the results in a pie chart here. As you can see, in this room we will have 139.4 millimeters of mercury oxygen, which is shown in green color, in orange color, 7.6 millimeters of mercury carbon dioxide, which is shown by yellow, 60 millimeters of water moisture, which is in gray, and 553 millimeters of nitrogen in blue. And you should always remember that adding up all gases in a container should come to total pressure equal to the atmospheric pressure that you have from the beginning. So adding these up, we come to 760 millimeters of mercury, which is the atmospheric pressure in the room. Okay, we talked about partial pressure of gases till now, and before continuing that topic, I would like to discuss a different topic, which is distribution ventilation of gases. When you have a container and you put a little bottle of a green gas, for example, in it, then you open up the lid of the inside bottle. The green gas will slowly, based on its characteristics, distribute to fill the big container, and finally it will get out of the container. This process is called gas distribution and is totally different from gas ventilation. Okay, as you see in this slide, it is exactly the same as the previous one, except that you have a vacuum fan outside the big container. So if you put a fan outside the container, it will vacuum the green gas. Therefore, it will reduce the time for gas distribution. And this process is called ventilation. In your lung, we have both systems, I mean distribution of a gas and ventilation. So my question is, why the lower lung or lower part of your lung has more ventilation compared to its upper part? The answer to this question is not given in the slides, and I would like to ask you to find the answer on internet or in books, or ask it from your colleagues. In this part, we have a combination of two topics: the partial pressure of gases and the ventilation of gases, which now come to the lung. Let us say dry air travels to trachea, where we have 47 millimeters of mercury water moist pressure. However, in equilibrium state, it doesn't have any carbon dioxide. As you can see in this table, the partial pressure of oxygen in ambient dry air would be 159 millimeters of mercury. We will have little or no carbon dioxide in air. In dry air, we do not have any water. We have about 600 millimeters of nitrogen, and the total pressure would be 760. But at moist tracheal air pressure, we will have different partial pressure for the same components. As you can see and you can calculate, we have 47 millimeters of mercury water moisture in trachea. So this partial pressure of water is reduced from 760 total pressure, and the remaining part would consist proportionally from oxygen, which would become 150 millimeters of mercury and 563 millimeters of nitrogen. And now we come to the most difficult part of our discussion, which is alveolar partial pressures. We came from outside dry air to the tracheal level, and then from tracheal level we are going to alveolar level. As you can see in the diagram on the left side, in dry air we have 21% oxygen and 79% nitrogen, which will result in 160 millimeters of mercury oxygen partial pressure and 600 millimeters of nitrogen partial pressure. This air goes to trachea and then goes to alveoli or lung. At lung level, we will not only have oxygen, nitrogen, and water, we will have also carbon dioxide with a total pressure of 760 millimeters of mercury. By using the formula that you had on slide 21, you should be able to calculate the partial pressure of gases at this level. But actually, we have different partial pressures. As you can see, we have 102 millimeters of mercury oxygen partial pressure and 571 partial pressure for nitrogen, 40 for carbon dioxide, and 47 for water moisture. So, considering same formula on slide number 21, we should have oxygen partial pressure of 21% multiplied by 760 minus 47, and the total result minus 40, which will result in 110 millimeters of mercury. Okay? And we come to the gray box. However, as you saw in the previous diagram, oxygen partial pressure level in the lung or alveoli is only 102 millimeters of mercury. We calculated 110. Why is it so? Please think over this topic, which is really pivotal, and then go to the next slide. As you saw in our previous example, we said that we are burning paper. When we burn paper, for production of each molecule of carbon dioxide, we should use one molecule of oxygen. But it is not the same in our body. In our body, usually by using one molecule of oxygen, only 0.8 molecule of carbon dioxide is produced, and some part of oxygen is used to produce water. Therefore, more oxygen is used and less carbon dioxide is produced. This is shown by a ratio called R, which is usually 0.8. Therefore, in our calculations on slide 21, we are consuming 40 over 0.8 or 50 millimeters of mercury of oxygen instead of producing 40 millimeters of carbon dioxide. It is a bit difficult to understand, but I'm sure you can understand it. So in our body, we can modify the formula on slide number 21, and we come to a new formula. In this new formula, you can see that alveolar partial pressure of oxygen is equal to initial partial pressure of oxygen multiplied by atmospheric pressure minus partial pressure of water moisture, and the total result minus partial pressure of carbon dioxide over the R ratio, which is usually 0.8. Or in our case, we can say that alveolar partial pressure of oxygen would be 0.21 multiplied by 760 minus 47, and the total part minus 40 over 0.8, and the result would be 100 millimeters of mercury. Okay, and this slide may be somehow sophisticated and will not be necessary for you as a medical student to know, but if you are very interested in alveolar gases to know them in detail, then I will recommend you to read this slide as well. We calculated alveolar oxygen partial pressure to be 100 millimeters of mercury, but we have 102 millimeters of mercury in the diagram on slide 25. We have 2 millimeters of mercury difference. And what is that for? You should know, as oxygen is more consumed than carbon dioxide to be produced, there would be 10 millimeters of mercury negative pressure in the alveoli. It would be replaced by fresh gas with 21% oxygen, and therefore 2 millimeters of mercury oxygen will be added to the above calculated oxygen as fresh gas comes to the lung. At the same time, about 8 millimeters of mercury is added to nitrogen pressure. As you can see, in trachea we had 563, and at the level of lung we came to 571. And this difference is because of the suction of fresh air, which has 80% nitrogen, which will become 8 millimeters of mercury nitrogen. Okay, and finally we have come to the final slide, which is self-assessment. Okay, you can design different scenarios and solve them for yourself. For instance, I have provided 2 examples, but I'm sure you can add some more yourself. For instance, in the first situation, what is your idea about alveolar partial pressures when we use 100 oxygen inspiratory oxygen? For instance, a patient is intubated and is consuming 100% oxygen, or he or she has a face mask with a reservoir bag and high flow oxygen, which will cause to consume nearly 100% oxygen. So what would be the partial pressure of gases in your alveoli in that condition? And in other question, we have asked what will be the condition if we climb a mountain. As you know, when you climb a mountain, the atmospheric pressure would not be 760 and it will be lower than that. Or sleeping in a hyperbaric capsule, it may have 2 or 3 atmospheric pressures. In those cases, what would be your opinion about partial pressure of gases in your alveoli? And thank you for being with me, and if you have any questions, I will be available with the email provided in the first slides. I wish you the best.